Okay. So here's a recap of where we're at. So the problem we're trying to solve is, determine if f is either constant or balanced. Now, we want to determine this with a single query to this unitary implementing f, which implements it in this very, particular way, which, if you think about it, is natural, which we saw earlier, which is in this way here. So this is how the unitary UF acts on the standard basis elements. Now, classically, even with access to such a function, you would take two queries to determine exactly if f is constant or balanced. The algorithm that we'll see only takes a single query, which is quite remarkable. Okay, so what can we try to do quantumly that it's not possible to do classically? Okay. So the problem classically was if we have access to such a mapping as it's written here, then whenever we input x to be equal to 0, we only get information about f of 0. And that's also true for the quantum case. If the first qubit is in the state ket 0, we only obtain information about f of 0. If the state of the first qubit is 1, ket 1, we only obtain information about f of 1. But crucially, neither of those inputs gives us information about both f of 0 and f of 1, which is what we need to determine whether f is balanced or not. And recall that the answer to whether f is constant or balanced is equivalent to determining the value of f0 XOR f1. f0 XOR f1. So what can we do instead quantumly if we want, to obtain information about both f of 0 and f of 1 simultaneously? Any ideas in the chat? Yeah, something with superposition. Yes, that's true. Lorraine is saying something about superposition. It's a very good insight that she's trying to figure out if both qubits need to be in superposition. That's yes, that's a very, very good insight. So let's see. So what about if we start? Yes, Anjali, yes, that's correct. We'd use the edge gate exactly. So what about if we start with the first qubit in the following superposition state? Okay, so basically the plus state, h applied to 0. And then the overall input, and when we leave the second qubit, so the y qubit as 0, okay, then the overall input would be this psi. Right? First qubit in the plus state, then 0. So overall, the state is just 0, 0, 1 over square root of 2, 0, 0, plus 1 over square root 2, 1, 0. Okay. What does that buy us? Now, if we try to apply the unitary u sub f to psi, and this counts as one query. Okay, so we're using up our one query. What we obtain is the following. The output, psi output, will be sort of uf applied to the state that we had before, like 0, 0 plus 1, 0. And what you obtain in the end is 1 over square root of 2, 0, f of 0, right? So, the way the UF acts, on the second line, the way the UF acts on this big state here is you can sort of decompose it as UF acting, on the individual terms of the sum. So first UF acting on 0, 0, and then UF acting on 1, 0. That's how you get to the last line. So 0 f of 0, and then 1 f of 1. right? Is everybody happy with this, with how, what we got at the end here in the last line? What if UF was acting on the y qubit? It is acting on the y qubit, but remember the way it acts, right? It maps, xy to x, and then y XOR f of x. So if y is 0, like if the second qubit is 0, which is the case here, right? Because we left it, from the start, we left the second qubit as 0, then there's no XOR. It's just f of 0 and f of 1. That makes sense? If not, I can clarify further. Mm-hmm. What if we switch the qubit with the, yeah. So if we switch the qubit with the ARMA, that's the case that we will consider in just a moment. Okay, so far, we've put the first qubit in a superposition, the second we've left it the same. Oops. Now, the nice thing is that the state that we got in the end contains information about both f of 0 and f of 1. That's a nice thing that we couldn't have got classically. However, okay, as it is, I guess Lorraine was already hinting at this before, but when she was saying, I'm thinking whether I should put both qubits in superposition. So the question I ask you is, from this state that we got at the end, is it actually possible to, just by measuring, extract information about both f of 0 and f of 1 simultaneously? Like what happens if we measure? So Lorentz says no. 50-50 probability, yes. So what do other people think about this? Suppose that we measured the state, what would we actually be able to extract information about both f of 0 and f of 1? Yeah, so the measurement collapse. So essentially, if you were to measure the state with probability, let's say you measure the first qubit in both, okay, or you measure the whole thing. That doesn't make a difference, right? So with probability 1/2, you would find that you are in the first, that the state is 0 f0 for the first branch. In which case, the whole wave function collapses to just 0 f of 0, and there's no information whatsoever about f of 1. So you learn f of 0, but you have no clue about f of 1. With the other remaining, half probability, you would instead get outcome 1 f of 1, which collapses the wave to 1 f of 1, and you learn f of 1, but you have no clue about f of 0. Okay, so this, seems to buy us something, this superposition, but actually not quite yet. Yeah, so this is the question I asked, whether we can extract information about f of 0 and f of 1 by measuring simultaneously. No, we can't get information about both. So, let's try a different approach, which Lorraine was suggesting. Let's not put the first qubit in a superposition. Instead, let's place the second qubit in a superposition state. Okay. In particular, let's, I guess this is, kind of giving you already a hint, but, let's initialize the second qubit as the minus state, for example. So 0 minus 1. And let x instead be, either 0 or 1. Okay, like not in a superposition, just get 0, get 1. So now in this case, our initial state is called it psi, is x in the first qubit, either 0, 1, and then a minus. And you can sort of compute this expression. You would get 1 over square root of 2 x0 minus 1 over square root of 2 x1 if you expand everything out. Okay, so now what happens if we apply UF to this state? Okay, so we're applying UF to whatever expression we got before, the initial state. Now again, UF by linearity, it acts on the first term, decompose it as acting on the first term minus whatever UF acts on the second term. So what you get in the third line is 1 over square root of 2x, and then you have a 0 plus f of x, right? Because the y qubit is now 0, minus 1 over square root of 2x, and then 1 plus or XOR f of x, because in the second term the y qubit is 1. Okay, and we can group this. We can, I hope you see this, we can sort of group this by kind of factoring out the first qubit is always in the x state. Okay, so we can rewrite this as 1 over square root of 2x, and then simply 0 plus f of x minus 1 plus f of x. Is this calculation, are you happy with this calculation? Is there anything I can review about this calculation? Yeah, I'll go over it one more time. So first of all, are we happy with the initial state psi being equal to this expression here, x0 minus x1? Okay, so applying UF, okay. So now in the second line here, by the way, do you actually see when I do this? Like, do you actually see that I'm highlighting? Okay, good. So now in the second line, I'm just plugging in, whatever we got before as the expression for psi, applying UF. Okay. Now this is the same as. Let me rewrite it. Oh wow, I think I'm gonna get lost here. Let me not rewrite anything. So this is in the third. The way we got to the third line is by linearity, right? Remember, by linearity, the expression in the second line is the same as applying UF to the first term, to the x0 term, okay, minus UF applied to the second term, the x1 term. This is just by linearity. Okay. Now, if we apply UF to the x0 term, okay, what we get is x. Remember that how UF acts, right? It maps xy to x, y plus f of x. Okay. So now y in this case is 0. Okay, so we get x and then 0 plus f of x. Then when UF acts on the second term, the x1 term, because the y qubit is 1, you get always x on the first qubit. That never changes. And you get 1 plus f of x. Yeah, XOR, yeah. So when I say plus, I always mean XOR. And so then to get to the last line, I'm just rewriting things because the first qubit is always in the state x, right? So I can kind of group things in the following way, right? Kind of doing the inverse of the distributive property. Okay, nice. Okay, so now notice here that our result depends specifically, whether we, this last term here in the last line, whether that's, an x and then 0 minus 1 or 1 minus 0, depends specifically on whether f of x is equal to 0 or f of x is equal to 1. Okay, there are two cases. If f of x equals to 0, then this last expression that we got will be, 1 over square root 2x, that stays the same, and then 0 minus 1, right? If f of x is equal to 0, which is the same as x minus. But if f of x is equal to 1 instead, we will have 1 over square root 2x, and then here the first term here will be a 1, and the second term will become a 0. So it will be 1 minus 0. So the only difference between the two expressions, in the cases f of x is equal to 0 or 1, the only two differences are a minus sign. Okay? In other words, we can summarize what we got here as saying the following. So we started with x minus, right? And then we applied u sub f. Okay. So what we discovered is that u sub f applied to x minus returns always x minus, except there's a minus sign in front, like a minus 1. And this minus 1 depends specifically on f of x. It's minus 1 to the f of x. If f of x is 0, this will be a plus 1. If f of x is 1, this will be a minus 1. So in some sense, our answer, the information about f is stored in the phase now. No longer in the ket itself, it's stored in the phase, right? So this is very crucial, and this is something that we'll use later. So it seems like we have gained nothing, okay? But we have observed something very nice, that if we start from x minus, we apply uf, then we are able to get a minus 1 to the f of x. We have no way of measuring phase, that's correct. So this so far is just an observation. And after James's lecture, unfortunately we have this hard constraint, but after his lecture, I'll get back to this and I'll show you how we can combine, the ideas from putting the second qubit in superposition like we're doing here, or putting the first qubit in superposition like we did just now, to get something that's actually useful. So now before I leave it to James, just make sure that this expression here is, everybody is happy with. Now, Lorraine is not happy.
So I am looking at the formula there for like the output, the first output in 0. So I've got the amplitude is fine. So we have the 0 ket minus the 1 ket, and you're saying that maps, or that goes to x ket times a minus ket. I don't know where you're getting that. How do you make that transition?
Okay. So the transition is that we had defined the plus and minus states as being
okay, thank you.
Remember the plus state was 0 plus 1 and the minus state was 0 minus 1.
0 minus 1. So we reverse the terms on the bottom one.
Yeah, on the bottom one we have 1 minus 0 when f of x is equal to 1. So that's basically minus, the ket 0 minus ket 1. So they're the same expression except the difference of a minus sign.
Okay, so shouldn't that bottom term then be x ket times a 1 ket, a plus 1 ket, a plus ket, I guess?
No, because one, if you multiply sort of 0, so the ket 0 minus ket 1, right? Multiply, so what we have on the first line here, multiply that by minus 1, right? You would get the minus 0 and the plus 1.
Right.
So that's a minus 0 plus 1. So it's right. So which is exactly what we have at the bottom.
But isn't that the same as our definition for a plus ket?
No, the plus ket, in the plus ket, the ket 0 and the ket 1 have the same sign. Like they're both plus.
I'm sorry, thank you.
Here, one of them is plus and the other one's minus.
I always have to write down all these things right where I'm doing the measurement, because otherwise I'm too confused. But thank you.
No, for sure, for sure. Yeah, yeah. So the difference is the relative phase, if you want, you know. In one of them, there's a -1 sort of relative phase, and it's the minus ket state. In the plus ket state, they have the same. There's, you know, the 0. There's no relative phase. There's both pluses.